If you've had an embarrassing fall lately,
Oh, God! No! Oh, my God!
you can thank gravity.
Hey, Ron. Hey, Billy.
Gravity is actually the weakest force we know. It's weaker than the pull of a fridge magnet. Despite this, it's responsible for everything from ocean tides to the formation of stars. It gives weight to every physical object and is the reason that planets and whole galaxies are attracted to one another. While ancient philosophers, architects, and mathematicians theorized about the phenomenon, Sir Isaac Newton's theory superseded them all. He deduced that anything with mass will attract anything else with mass. The more mass, the stronger the attraction. The more distance between the objects, the weaker the attraction. Newton's theory prevailed until Albert Einstein introduced his theory of general relativity. Einstein argued that gravity was not a force. Instead, it was a distortion or warping in the shape of space-time caused by massive objects such as the planets and stars. Today, Einstein's theory remains scientists' best explanation of gravity. Einstein also predicted the existence of gravitational waves in his general theory of relativity. These waves are ripples in space-time caused by violent and energetic processes, such as colliding black holes or supernovae. It was only in 2015, though, that researchers first detected gravitational waves, proving Einstein's theory right. We couldn't live on Earth without the presence of gravity. It pulls us toward the center of the planet and keeps us tethered. Gravity also allows Earth to hold on to its atmosphere. The Sun's gravity keeps us in orbit at the right distance to support life, and gravity from the Moon and Sun is responsible for the rise and fall of ocean tides. It might come as a surprise to you that gravity isn't the same everywhere on Earth. It's slightly stronger over areas with more underground mass. The highest gravity has been measured at the surface of the Arctic Ocean, while the lowest gravitational acceleration is on Mount Huascarán in Peru. Gravity also varies from planet to planet. Weight is a measure of the effect of gravity on mass. On Earth, for example, you weigh around 3 times more than you would on Mars. On the International Space Station, gravity is about 90% as strong as it is on Earth. Microgravity, or conditions in which gravity is extremely small, can be dangerous to the human body. Without Earth's gravity, weight-bearing bones lose 1 to 1.5% of mineral density per month on average during spaceflight. Astronauts may also lose muscle mass faster in microgravity than they would on Earth. Sometimes bone and muscle atrophy can even occur. Microgravity can cause an increase in the cerebral spinal fluid in the skull cavities, putting pressure on the eyes and causing vision problems. It can also lead to an increased risk of developing kidney stones due to dehydration. These effects don't all disappear upon returning home. Astronauts need to readapt to Earth's gravity. This transition can affect spatial orientation, head-eye and hand-eye coordination, balance, and locomotion. Some astronauts may even experience post-flight orthostatic intolerance, where they are unable to maintain their blood pressure when standing up, which can lead to lightheadedness and fainting. Thankfully, NASA is already hard at work on the issue. A nutritious diet and adequate exercise are important. Astronauts on the ISS, for example, exercise more than 2 hours a day. NASA is also researching drugs that treat bone loss in astronauts, as well as people on Earth who suffer from osteoporosis. These studies and more will be key to developing the best protocols for space travelers to the ISS, the Moon, and beyond.